Good evening, everybody, and a very warm welcome to this special event hosted by the Hunter Branch of the Royal Society of New South Wales. And tonight we're featuring Professor Jason Sharples from the University of New South Wales, who will be talking to us about bushfires. In order to formally open this meeting, I would like to acknowledge the traditional owners of the lands on which we stand and pay our respects to elders, past, present, and emerging. In the case of those of us who are here in the city of Newcastle, this addresses the Awabakal and Worimi people, but of course I acknowledge the traditional owners of the lands from which you are joining us via this webinar video link. Before I hand over to Professor George Willis to formally introduce this evening's speaker, I would like to thank Professor Natalie Tamwatana for both orchestrating this event and for responding so quickly and efficiently to the challenges thrown up by COVID. And in the same breath, I also like to acknowledge the help and support we've received from Stuart Midgley in order to make all the technical arrangements for this presentation. And finally, I would like to thank Associate Professor Egbelakin for agreeing to host this evening's question and answer session. So with all of those important thank yous in place, it's now my great pleasure to ask Professor George Willis to introduce tonight's guest speaker.
Thank you, John. It's my great pleasure to introduce Jason Sharples tonight. Jason did a Bachelor of Science and Bachelor of Mathematics with honours with us at the University of Newcastle, finishing in 1995, and he was awarded the University Medal. He was one of 3 Jasons we had that year, and they were all excellent mathematicians. He went on to do a PhD in general relativity at the University of Canberra, I think, with Robert Bartnick. And but since then, he's moved on to work on bushfire modelling, and that's what he's going to talk to us about tonight. He's enjoyed great success in that field, and he has more than 65 journal articles and 54 conference proceedings, but more significantly perhaps he's had recognition for his research with plenary lecturers at places like Los Alamos and the Australian Academy of Science, and he's received substantial funding from the Australian Research Council, from the New Zealand government, and from industry partners. He's now leads the University of New South Wales bushfire research group, and in his research on bushfires, he's made significant contributions to our understanding of bushfires, both through the understanding the weather that precedes bushfires and leads up to them, and then once they start, he's done a lot of work on modelling on how they spread. And his impact, the impact of his work can be seen by the fact that a number of the concepts he has introduced and developed in his research have now been taken up in bushfire centres throughout the country and increasingly around the world. Following the bushfires in the summer of 2020, he was an expert witness at 3 inquiries that were held afterwards, including the Royal Commission, and his advice was reported in the reports of all of those inquiries. I think that's really a good indication of the significant impact that his research is having. Now, before I hand over to Jason, I would just encourage you to ask any questions. If you have any questions, they can be typed into the Q&A section during the talk, and then they will be answered at the end. I think you'll find a button on your screen. If you press that button, you can type your question in. So now, please, Jason.
Thank you very much, George. Right. So yes, thank you very much for that, for the introduction, George, and thanks for the invitation to speak tonight. I should also start out by acknowledging the country that I'm on. I'm on Ngunnawal country down here in Canberra, although I did grow up in a Awabakal country and a Bundjalung man to boot. So I'll acknowledge all those three nations tonight. So I guess what I really wanted to do tonight, I mean, there's these terms in the title of my talk here: extreme bushfires, the age of violent pyroconvection. So I'm going to explain what I mean by those, and then that's hopefully just going to lead into a discussion of the sort of research we've been doing over the last 10 to 15 years, and what that has actually told us about the sorts of fires that we got, say, in the Black Summer that George mentioned already. All right, so I think I'm just going to launch into it, and I always start out by saying that the best way to explain to somebody what an extreme bushfire is to start out by explaining what it isn't. And clearly, what we have on the screen there is not an extreme bushfire. The reason I show this, though, is that this is Alan MacArthur and his group of researchers from the CSIRO back in the 60s, working on Black Mountain, which is not too far from where I am here in Ngunnawal country. But the way they were approaching understanding fire and understanding fire behaviour then, as you can see, were through these experimental burns. Now, experimental burns, you don't want them to get away and cause damage, so they typically occur under relatively benign conditions, okay? So not too hot, not too dry, not too windy. But the idea is to set the fire like they have there, measure the environmental conditions under which it's burning, and then make some correlation between the observed fire behaviour and the environmental conditions that were observed. And this has been a very successful, very widely adapted approach to understanding bushfires. It's the approach which underpins, for example, the roadside fire danger signs that I'm sure everybody is familiar with. Okay, so the numbers and the equations which underpin that particular warning system mostly derive from the sort of experiments that you're seeing in that photo there. Now, as I said, that's all well and good. This has been very successful in terms of communicating fire danger to people. But when we're talking about extreme bushfires, we're really talking about something which looks quite a bit different from the picture on the screen. And I'll just show what we're talking about. We're talking about things like this. Okay, so this is the Creek Fire in California from last year, late last year. And so what we see now when we look at this, first few things you'll notice. First, we're a long way back from the fire now. You can't actually see any flames. We're up in an aircraft, and we're really taking a long range view of the phenomenon. Okay, the phenomenon itself doesn't really resemble a fire as much as it probably resembles something like a thunderstorm. Okay, a lot of these things look like volcanic eruptions, but you've got this phenomenon now, which is really more of an atmospheric event rather than the type of surface fire that we saw in the previous slide. So that was one from last year in the States, but we can draw, look back in the recent history and find any number of these events. Okay, so they all have this similar sort of structure to them, sort of the darker smoke down the bottom of the plume, which then transitions to this bright white cloud. And you can see that in each of these examples here. And I'll talk a little bit about what's going on there in a second. Okay, but yeah, the other thing to notice here is all of these fires are post-2000, and I'll come to that as well. Okay, but generally when we're thinking of an extreme bushfire, we're thinking of something which looks like this. The real key concept to understand extreme bushfires is this concept called pyroconvection. Now really, pyroconvection, pyro means fire and convection is just the ordinary sort of movement of air. So when we're talking about pyroconvection, we're really talking about movement of air driven by buoyancy, which is created by the heat of the fire. Okay, so we can see pyroconvection in action in this photograph here. So this is actually a cane fire, I think in Hawaii, so an agricultural fire. But it has all the essential features to it. You can see that the fire is burning. and that's causing hot air to rise. This is the buoyancy moving the air. As that hot air rises, what then has to happen is you have to draw in air from the surroundings to replace the air that's rising. And this is really the first, I guess, instance of where you can start to see a fire starting to create its own weather, which is a term that's used a lot these days. People talk about fires creating their own weather. That's kind of happening there already. The other thing you can see in this photograph is you can see this sort of layer in the atmosphere where below which you've got the dark smoke, and then above you've got this sort of white cloud forming. So this layer is actually where the moisture, which is in the plume of the fire, just a thing to remember is that when you burn vegetation, it releases moisture as well. So you have water vapor in the plume. Once that water vapor reaches to the level where it condenses into liquid droplets, then you start to get a cloud forming, okay, just like you do with an ordinary cloud. If it was an ordinary cloud, we refer to it as a cumulus cloud, but because it's being driven by fire, we refer to it as a pyrocumulus. So the thing really important to note is that when we talk about pyroconvection, we're talking about something which occurs in association with any fire. Okay, so everything from a lit match all the way through to the sorts of fires we had on during the Black Summer. These involve pyroconvection. It's just this buoyant movement of fire heated air. The other thing to realize is that pyrocumulus are not really an uncommon feature in bushfires. Okay, so this is, as I said, an agricultural fire, nothing too serious, but still you're developing this pyrocumulus cloud on top. And you'll even see these things form over on relatively small prescribed burns. And the thing to remember, or thing to note, is that they're really not dangerous in general. Okay, so when you just have this level of pyroconvection going on, generally not too much to be worried about. The difference we need to or the distinction we need to make is between ordinary run-of-the-mill pyroconvection like we see here and what I refer to as violent pyroconvection. Okay, so this is one of the terms that was in the title of my talk. So I'll spend a little bit of time just to talk about what I mean by that. So by violent pyroconvection, we're really talking about this angry-looking sort of convection that you're seeing in this photo here. Okay, very strong, expansive updrafts. The flows involved with this sort of development is highly turbulent, and it extends high into the atmosphere. So whereas in that last picture in the cane fire, the plume was only going up a few hundred meters, maybe a kilometer, when we have violent pyroconvection, the updrafts can be so strong that these things can extend up to 10, sometimes 15 kilometers up into the atmosphere. The implications of these things, or this violent pyroconvection for fire behaviour, is that you tend to have this stronger coupling between the ground and the atmosphere. Okay, so the fire becomes almost like an atmospheric process, and you develop these storm-like characteristics. So you get stronger, more erratic and unpredictable winds. The fire plume can actually start to mix down dry air from aloft towards the surface, which then has implications for drying the fuels out and things like that. And you also have increased potential for transport of embers, okay, burning bits of material. They get lofted up into these plumes and then can be deposited downwind quite a distance, kilometres or tens of kilometres even in some cases. So this really, putting these ideas together led us a few years ago to really trying to figure out a precise definition for what we mean by an extreme bushfire. And so the definition that we ended up publishing in about 2016, I think it was we said that an extreme bushfire is a fire which exhibits deep or widespread flaming, I'll get to that in a minute, in an atmospheric environment conducive to the development of violent pyroconvection. And these events will often manifest as towering pyrocumulus, pyroQ, which reach high up into the atmosphere, or in some cases, the worst cases, pyrocumulonimbus. Now, pyrocumulonimbus is really, literally, if you take the terminology, it's fire thunderstorm. So I talked about a pyrocumulus forming when the water vapor reaches a level where it condenses into moisture. If that then rises higher into the atmosphere, it can reach the point where it'll turn into ice. Okay, and you'll start to get ice rubbing together, forming electrification and a thunderstorm. Okay, so when we have a pyrocumulonimbus, we're really talking about a fire plume which is developed into a thunderstorm. Okay, and that will behave, very similarly to a thunderstorm. The way I always describe it is to say, think of a thunderstorm where you've got sort of erratic winds, sheeting rain, and all the rest. Take the rain out and replace it with embers. That's sort of what it's like being inside a pyrocumulonimbus. So the key concepts here are these ones of deep and widespread flaming and this atmospheric environment conducive to the development of violent pyroconvection. And I'll talk about that in a little bit as well. What we're really talking about, though, is we're talking about a fire which is coupled with the atmosphere well above the surface layer. Okay, this coupling, now the fire is generating the weather is feeding back on the fire and influencing its development. So this coupling now has the effect of modifying or maintaining the fire's propagation, and that can happen through these strong winds that can happen, the mass spotting associated with ember transport, and also things like lightning coming from an electrified plume. The actual fire behavioural aspect of it is interesting, and it's something we've researched a lot. But what we find is that the widespread flaming that we talk about here in the definition often results as a consequence of what we refer to as dynamic fire behaviours, and I'll show some examples of that in a few slides' time. Just before I move on, just wanted to make a bit of a distinction or a clarification between a couple of terms that are used. So I've explained what an extreme bushfire is. You hear the term megafire used a lot in the media these days as well, and I think it's important to make the distinction between an extreme bushfire and a megafire. I mean, a megafire is really defined by the size they end up burning, the amount of area they end up burning, and also the amount of resources that go into suppressing them. Okay, so really, if we think of it like that, they're an issue that arise from fire management doctrine, long-term changes to the vegetation across certain landscapes. And we're really talking about fires which can burn for a long time, absorb a vast amount of resources and burn a large area. So the Gospers Mountain megafire is a good example of that, burnt for something like 80 days and was the largest burnt area we've ever experienced on record. When we talk about extreme bushfires, we're not necessarily talking about the same thing, okay? And as I said, we've taken great care to define an extreme bushfire as a fire which involves this strong coupling with the atmosphere and exhibits these dynamic fire behaviours. So if we think about those two different definitions, then really extreme bushfires and megafires aren't related beyond the fact that in some instances, a megafire will episodically exhibit extreme bushfire characteristics. Okay, so an extreme bushfire will have a lifetime of a few hours at most, whereas a megafire can go for weeks or months. However, much of the significant impact that a megafire will occur during its lifetime will occur during these episodes of extreme bushfire development. So why do we care about extreme bushfires? Well, as I just said, it's because most of the impacts that are exacted by these things happen during these episodes of extreme bushfire occurrence. So here's an example of the Tubbs fire, which was a fire in California, October 2017. At the time, it was the most destructive wildfire in California's history. And you can sort of see the amount of damage it does. Billions of dollars in damage, 150 kilometre squared area burnt, thousands of structures destroyed, and multiple fatalities, 43 fatalities. But you can see these sorts of things, when they roll into the urban edge, they take out, if not everything, like here, then extensive damage. Just before I move on, I just wanted to point out in this photo, because this will come up again later on, despite the fact that pretty much every single house is burnt to the ground here, you'll notice that a lot of the trees, like these guys down here and here, still have sort of green canopy intact. Okay, and it gives you a bit of in indication to the way that the fire has impacted that urban edge, and in particular the role of embers, which I'll talk about in a second. So I mentioned that the Tubbs fire at the time was the most destructive wildfire in California's history. Currently, it's the second most destructive because it was actually surpassed in its level of destruction the year after by this monster here, which is the Camp Fire. So it's the current most destructive, although 2020 fire season in California gave it a good run for its money. But you can see the numbers involved are sort of by water in billions of dollars, hundreds of square kilometres, and thousands of structures destroyed. High impact events. Of course, we've had our own chain of events recently. The 2019-20 season, known as the Black Summer. I probably need to check this figure because it probably needs updated, but certainly hundreds, over $100 billion worth of insured losses. 18,000 kilometres squared. Okay, that's sort of up there, approaching unprecedented levels. Thousands of structures destroyed, billions of animals. 34 fatalities was tragic enough, but what a lot of people don't realise is that in addition to those 34 fatalities, there was over 400 smoke-related deaths from these fires, and you can see that in the animations going there. The amount of smoke generated by these fires is staggering, and a place like Canberra, where I live, which is normally renowned for its very good air quality, during the Black Summer was actually recording the world's worst air quality because of the smoke impacts. So they're not to be forgotten. They're really significant. Okay, so I hinted at this before, but one of the characteristics of extreme bushfires is that they don't tend to propagate across the landscape in the way most people tend to think about the way fires propagate. Okay, I think most people, when they think about a fire spreading across the landscape, they think of a line of fire or flame moving in a fairly orderly progression across the landscape, unburnt fuel ahead of it, burnt fuel behind it, and this thing just sort of evolves across the landscape in a fairly orderly manner. Extreme bushfires tend not to do that at all. You can see here, this is the 2003 McIntyre's Hut fire impacting the western edge of Canberra. This is the suburb of Duffy. But what you can see here is that there's really not a lot of flame at all visible. Okay, the main thing driving the fire, as you can see here, are these dense sheets of embers moving across the ground. And it's not until the embers move in and hit the shrubbery around the houses that you start to see flames igniting, growing, and then impacting the houses. Okay, but it's a very different mechanism or a very different form of attack on the urban edge. And it's kind of interesting because when you think about things like the Australian standard for building in bushfire-prone regions, that's all predicated on flames being present, and it's the radiation from the flames which set your house on fire. What these sorts of examples indicate is that nothing like that is really happening. It's embers are the dominant bushfire attack mechanism. And just a couple of other photos. These are also from the Canberra fires in 2003. Just to, I guess, hammer home that point, you have the houses burning down, but all the trees still pretty much intact around the place. Okay, so it's these embers sort of sheeting along the ground, hitting the shrubbery around the house. You can see flames starting to spark up there, which then go on to burn the house down. But it's not actually radiation from the flame itself. It's these embers which set things off. All right, so hopefully everybody's got a reasonable idea of what I mean by an extreme bushfire now. I'll just move on to this sort of next part of the title, and I sort of say, the age of violent pyroconvection. What do I mean by that? Well, this term, the age of violent pyroconvection, was really coined in response to a term that was coined by a fire historian called Stephen Pine, very famous fire historian from the States. Back in 2015, he wrote a famous essay where he coined the term pyrocene. And what he was really trying to convey with this term was trying to describe the epoch of history, or deep history, I guess, in which humans have shaped the world through their use of fire. And he was sort of saying, making the point that, you know, the Anthropocene itself can probably be viewed as a pyrocene, because fire has always been a tool that humans have used. However, Rick McRae, my close colleague that I work with, upon reading Pine's essay, very quickly suggested, well, we seem to have actually entered a sub-epoch, which he referred to as the age of violent pyroconvection. And what he was really trying to get at here was to make the distinction between before and after what appears to be a tipping point in the prevalence of these types of fires. So I can give you an idea of what I mean by that. So this graph here, what we've done, this is joint work with a whole bunch of people around the world. Basically, this is a catalogue of pyrocumulonimbus events, so these big firestorm events in Australia. Okay, they only go back to the start of the satellite record, which is about 1978, because it actually involves using satellite data to confirm that one of these things has occurred. But what we can see is, you know, going from about 1983, this is Ash Wednesday, up until about the late 90s, mid to late 90s, and then into the early 2000s, there wasn't a great deal happening. And then suddenly we've sort of entered this era where we're getting, you know, at least one, but sometimes it's, you know, some years multiple pyrocumulonimbus events, which, you know, didn't seem to be happening back in this part of the graph. Of course, you can see here the influence of the Black Summer on the totals involved. So if you think about between 2000 and 2018, there's about 46 of these events. In the Black Summer alone, we had about 35 events. So we almost added another 50% to our record. And you can see here, if you just sort of fit a basic exponential model, that's not looking great. But yeah, you can sort of see the change is around about this period here, where some would argue that we've sort of crossed a tipping point, and we've now entered in this new age where we get these violent pyroconvective events with fairly, you know, in fairly regular succession. Not just us. This is some statistics from the Western United States, California in particular. This was a recent cover of the International Association of Wildland Fires magazine, Wildfire. California 2020, worst fire season ever, again. And you can just see here is a list of the 12 largest wildfires in California and the 12 most destructive wildfires in California. And the red ones were just from the 2020 season. And if you look even closer, you'll see that there's really only one, the tunnel fire here, that didn't occur post 2000. So again, an indication there that, you know, things may have changed. And even in places like Europe, this is a big fire in Portugal in 2017, their most deadly fire that they ever had. First time a pyrocumulonimbus was recorded in Portugal, as far as the you know, the international group that I mentioned has identified, and just, you know, 63 or 62 people killed in this fire, you know, in a very short succession. That's just a quote there down the bottom from the mayor of the region that was affected, who just noted that, you know, this doesn't seem real. This is really something out of the world as far as people's experiences are concerned. All right, so having hopefully given you a good idea of what an extreme bushfire is and why we might be concerned about their prevalence in this, what appears to be this new age of violent pyroconvection, what do we do about it? Well, what we've been doing about it is really trying to understand how these types of events come about. Okay, so I sort of tell a lot of people that, you know, what we try and do is we try and understand how small fires turn into big fires. And of course, that's not a new thing to consider. But if we look at the way people have considered the problem historically, then a lot of the research that's gone into trying to understand how these extreme bushfires develop has been through consideration of mainly weather and other atmospheric factors. So the key one that people tend to look at is how hot, dry and windy our surface meteorological conditions are. So that roadside fire danger rainbow that I showed that MacArthur helped develop. It's sort of underpinned by something called the Forest Fire Danger Index. And basically that's an index of how hot, dry and windy the surface conditions are. In addition to that, people also look at what would be typically lower atmospheric conditions, but also some mid-level atmospheric conditions. Examples of that are the Haynes or C. Haynes index, or the new PyroCB firepower threshold that has been developed by the Bureau of Meteorology. Doesn't matter if you don't really know what they are. All they're trying to do is really tell you or give you an indication of how likely your plume is to develop through those lower and mid-level levels of the atmosphere, and getting up to the points where you can get your plume condensing into cloud and then into thunderstorms type behaviour. Okay, so this is sort of telling you a little bit about how you expect your fire to burn, and this is telling you about how you expect your plume to rise through the atmosphere, essentially. Now, the interesting thing is that, despite the fact that it's well appreciated that these extreme bushfires that we're talking about are truly, the way to categorise them, or the way to think about them is, as a coupled fire atmosphere event, a lot of the focus has been on the atmospheric side of things and not a lot on the dynamics of the fire. Okay, so I guess that's kind of where we've done a lot of our research, is to sort of go back and say, well, okay, we've got all these atmospheric things, but then, what role is the fire itself playing in these sorts of events, and the escalation of the fire? So this is an interesting graph here. There's a lot going on, so I'll just take a minute or two to explain it. So what we've got here is basically the C. Haynes index. So this is our potential for our fire or our plume to move through the atmosphere vertically on the vertical axis. And we've got our surface fire behaviour in the Forest Fire Danger Index on the horizontal axis. The themed or coloured sort of thematic shading underneath just tells you how frequent conditions are. So you can see the most frequent conditions are low FDI and a C. Haynes value of around about 2, which is not high. And, events out here are pretty rare. And we've got this sort of concentrated area of increasing or decreasing frequency in the red to white region there. The other thing going on in this graph is we've got all these points. Now, all these points are individual fires. Okay, and what we've done is we've split these into 2 groups. The red points are ordinary wildfires, standard wildfires, which didn't develop into pyrocumulonimbus, and the white points are the fires which developed into pyrocumulonimbus. What we've then done to each of those points is we've given them a shape and an outline colour, depending on, okay, so the shape tells you what sort of landscape that we're burning in. Square is flat, and up to your really rugged rolling hills and steep mountains are the crosses and triangles. And then the outlines, the green is fires which have burned in forested terrain, and the black outlines are fires which have burned in non-forested terrain, so like grasslands and things like that. So what you can see if you just cast your eyes across all these points is that a lot of the white points, the pyro-CBs, well, they're all crosses and triangles. There's one there that's a square, one's a diamond, but most of them are crosses and triangles. So even though you're getting these things occurring at relatively low forest fire danger indices, so this is just moderate fire danger here where this pyro-CB's occurred, they tend to happen above a C. Haynes of about 8, so you do need some level of, you need your atmosphere to be conducive to this plume development going on, but really the atmospheric conditions at the surface can still be fairly mild and you can get these things happening. What seems to be a really distinguishing factor, though, is the type of terrain and the type of fuel that it burns in. So really this graph, if you think about it, really singles out terrain and fuel as distinguishing factors, and terrain and fuel are both things we know to influence the way a fire behaves. And we can see it in these 2 pictures here. So what we have here is a fire which is from 2018 or 2019, I think. Recent, 2018 it must have been. Yankees Gap fire, which burnt down the south coast of New South Wales. These are two scans of the fires in different stages of development. They're about 50 minutes apart. Okay. What we can see here in this one is we've got this little fire which is ignited, and you can see that despite the fact that the wind was blowing out of the northwest, the fire has actually spread back up the hill opposite to the wind, hit this ridge line, which you can see there in the white dotted dashed line. It's also here in the red dashed line, and it's actually gone across the wind, okay, almost 90 degrees to the wind across that ridge, jumped down to the next ridge line and gone across it as well, 90 degrees to the wind direction. So this isn't normally what you expect a fire to do. I mean, normally, if this was flat terrain, for example, the fire would just spread in the direction of the wind. But because we're in rugged terrain, we're in forested landscapes, you can have these extra processes kick in, which are dynamic processes. They involve interaction between the wind, the terrain, and the fire itself, which will actually spread the fire in a direction which is totally unexpected. So we've actually been able to, so that's 1.5 kilometres, and then I think it spots down about 4 kilometres. So all up, this area that you see involved in fire here is probably of the order of 300 or 400 hectares. Okay, so 300 or 400 hectares in the order of 50 minutes is pretty substantial growth of a fire. We've been able to get a good understanding of what's going on when these sorts of events happen. So that spread across the wind, we now understand as being due to something we call vorticity-driven lateral spread. You can see it happening in an experiment here that we did with our colleagues in Portugal. The fire was ignited down the bottom of the slope here. The wind is coming straight out of the page towards you. So the fire is burning back up the slope against the wind. And then when it gets to the ridge, it spreads across the ridge very, very quickly, just as you saw in that the scans. This is a computer simulation showing you exactly the same thing. So the fire starts down the bottom, spreads up, and then spreads sideways when it hits that ridge line. So that's what it looks like in the lab. That's what it looks like in a computer simulation. We can also see what it looks like in real cases. Let's mute that. So this is a fire from Black Summer. And the idea is to really note the rotation in the plume here, which is the vorticity that's referenced in vorticity-driven lateral spread. And again, you can see the same thing here, and you can see the effect that it's having on the development of the fire. Particularly here, if you have a look down, you can see that you've got spots all through this bit of the terrain, and then they all coalesce and give you this area of what we call deep flaming. So I mentioned the word deep flaming. What do I actually mean by that? Well, again, just to make the distinction, if you think of ordinary frontal fire propagation, then you have this line of fire, unburnt fuel ahead of it, burnt fuel behind it, but then you have this sort of relatively contiguous boundary between the unburnt and the burnt fuel. When we have extreme fires, you get this deep flaming, which probably looks a little bit more like this. Excuse my bad PowerPoint art, but I think it gives you the idea. You're talking about large areas involved in active flame, lots of spots which then coalesce with each other and produce this sort of behaviour. So what we've found in a lot of the fires we've looked at is that when you see these escalations in fire behaviour and you start to get your strong pyroconvection kicking in, you often have this spatiotemporal link with instances of deep flaming. Okay, and you saw that in those scans that I showed you a few slides back. So from that point of view, to try and understand what causes extreme bushfires to develop, okay, we need to know something about the atmosphere, but we also need to know what's the potential for the fire forming deep flaming. And so what we've been able to identify through our research is several triggers which can cause deep flaming: strong winds, wind changes, vorticity-driven lateral spread I've mentioned, mass spotting and fire coalescence. That's when you have lots of fires which just sort of join up into one big flaming zone. A process called fire eruption. And one we've added fairly recently to the list is what we refer to as overzealous use of incendiaries. The thing to note, though, is that all except two of these involve dynamic fire propagation. Okay, so dynamic fire propagation is propagation which is actually driven by interactions between the fire and the environment around it. And the tricky thing about dynamic fire propagation is it's subject to threshold behaviour. The other tricky thing about it is that we don't really know much about it, and we don't really have any operational capacity to account for these behaviours at present, although we are slowly improving matters. Just to give you a quick example of what I mean by threshold behaviour, this is the Wombalong fire from 2013. What we're seeing in these two images is the fire in two different stages, one under the influence of winds from the north-northwest, so more sort of coming out from this direction, or to your right to left. You can see this bit of the fire is not really that active. Okay, this is an east-facing slope here. So the fire's not very active. However, as the winds shift around to the west, so they're coming more out of the page towards us, you can see the escalation in the fire behaviour associated with that. So as the wind slowly sort of moves around, it crosses that threshold and starts these extra dynamic fire behaviours to kick in. I'll skip over this because I'm running short of time. But all we're talking about here is plumes which can attach to the surface of a canyon. Okay, so this is again some experiments I did with our Portuguese colleagues in a place called Lusa in central Portugal. So what we do is we form a V-shaped canyon and we set fire to it and see how the fire behaves. As a special guest, I was given the privilege of viewing the fire behaviour from the top of the canyon. So that was my view during the experiments. And you can sort of see the fire behaviour there. The thing to note here is that when the slope was 30 degrees, this is me at the top, when the slope was 30 degrees, you had sort of two fire fronts which moved up the steepest slope. Whereas if we increase the inclination of that canyon a little bit more, then the fire ran straight up the slope, and you can see me getting quite hot there. If you look at the slide-on view, it's even more telling. For the 30-degree slope, the flames are going up, so the plumes are detaching from the surface. Whereas if we have a slightly steeper slope crossing the threshold, then the flames don't detach from the surface, they lay down and you don't actually see them until they erupt on the top of the canyon, hence the term eruptive fire spread. So why is deep flaming important? Well, this is some recent work we've done looking at the role of how the area and the shape of the fire influences the ability of the plume to reach high up in the atmosphere. So what we've got in these three panels is three different fires. Okay, one's just treated as a circle, so you can see the shape of the fires here, circle of 1 kilometre radius. In the one in the middle, we've got a rectangular fire with a 4:1 ratio. And in this one here, we've got something which looks more like a fire line, a rectangle, but in a 64:1 ratio. And you can see that despite the fact that all the fires are releasing the same amount of energy, they have the same area, it's just the area is being distributed differently. When you have your big blob of fire, the plumes can reach much higher in the atmosphere. Here, it's actually getting up into the stratosphere. Here, it's just poking up into the stratosphere. But for our line of fire, it's not getting anywhere to the stratosphere at all. And this is to do with the fact that if you have a line of fire, a source of heat which is fairly thin and spread out, it's easier for the atmosphere to sort of tease that apart before it gets too high. It mixes the heat out. These are just some animations. I'll just let those run. But again, this is the same idea. Our circular fire, our rectangle 4:1, and our 64:1 rectangle, but with different wind speeds in each of the different rows. But you can sort of see, the more the fire that resembles more of a deep flaming situation is reaching higher in all of these cases. Okay, if it reaches higher, then it has more chance to get to the point where it condenses, glaciation occurs, and so you're more likely to have these things develop into firestorms. All right, I'm running short on time, but just wanted to finish by just looking at a few of the implications for extreme fire development, and also some of the challenges that we face. And of course, obvious implications are firefighter and community safety. If I had another hour to talk, I could go into that in detail. Likewise, we could talk about cultural burning. I won't really have time to talk about that. So the two that I really want to focus on tonight are the role of fuel load as opposed to fuel dryness and fuel availability, and then this sort of spectre of climate change and how that factors into it. So I think most people are aware there's been a a fairly active debate going on since the Black Summer, and indeed going back for years, about the role that fuel loads play in driving these large fires. Okay, and there's always this sort of people sort of saying, there should have been more fuel reduction done. If we had have managed the fuel better, then we wouldn't have these things. But this is from the New South Wales bushfire inquiry report, the independent inquiry. And what this shows is that, despite the fact that fuels were high, they weren't really any higher than they have been for the last 30 odd years. Okay, so if we want to think about fuel load as a factor, it doesn't seem to be really something which stands out as a distinguishing factor as to why we got such a bad season in 2019 as opposed to previous seasons. And indeed, the report sort of notes that, when we actually look at this in detail, the fuels were on average no higher than they have been for the last 30 years. And it was really things like fuel dryness and fuel availability, which allows the fire to burn more readily, which appear to be the more important factors contributing to these events. That sort of result is echoed in work like this, which is some colleagues at the University of Melbourne. So what we're seeing here in this graph is just looking at crown fire incidents, so when fire gets up into the crown of the trees, and just looking at what environmental variables are best at predicting the occurrence of crown fires. And the interesting thing you see is that fuel load, bark, elevated and surface fuel load, are the three lowest in terms of importance to predicting crown fire occurrence. More important are things like ruggedness, slope. Okay, so these are our terrain drivers coming in again. But the most important ones are these things like the moisture content of the fuel, okay, dead fuel moisture content and live fuel moisture content. And really, we've known probably for 30 years or more that fuel reduction has a diminishing effect as your fire weather deteriorates. Okay, so as your fire weather becomes more extreme, the effects that might have won you a bit of an advantage under more benign conditions tend to go away. And you can see that here as well. Okay, so this is just a graph. I've got the red bars showing you the number of firestorms or pyrocumulonimbus that occurred during Black Summer. And the black trace here is just a number which is indicative of the moisture content of dead fuels. And you can see that the days where you're getting these red bars poking up, the days where you're getting these firestorms, all coincide with days where you had your fuel moisture index, this measure of fuel moisture, below a critical level. Okay, so this is dry fuels again, being a sort of a distinguishing feature of driving these sorts of events. Of course, there's the broader climatic factors. If you look at the amount of actual fire power that's emitted by these fires, you can see something like FFDI and the fuel moisture index are really giving you really low fuel moisture index is associated with high fire power release, which is again these sorts of large extreme bushfire events that we're talking about. We can also get insights into the role that fuel plays or why it becomes less important through some of the modelling we've been doing. So this is work we've been doing through the Bushfire Natural Hazard CRC with our colleagues at CSIRO Data 61, James Hilton in particular. So what we've done is we've actually developed models which allow us to model the interaction between different parts of a fire. Okay, so this is all the mathematics here, don't worry about that. But the sort of thing it then enables you to do is say if you've got two fires starting here, it will actually enable you to model the influence that each of those fires has on each other. Okay, and remarkably, it's even able to model very basic scenarios which you haven't been able to model before, because if you think about this curved shape of a fire line, which evolves naturally when you have a wind driving it, that actually wouldn't happen unless there was interaction between different parts of the fire line. So we're actually now able to model these sorts of things. The interesting thing though is when you use these models to investigate what happens when you have lots of spot fires burning next to each other, these two top panels here tell you what's happening when you've got this interaction between the fire lines turned on, and the bottom ones tell you what's happening if you've got it turned off. And so what you can see is when you've got the interaction turned on, you have a lot more red going on here, so your fire is a lot more intense. Now, this is despite the fact that in both of these scenarios, the fuel load is the same. Okay, so it's not so much the fuel load which is giving you the extra intensity, it's the interaction between the fires. which gives you that extra intensity. So even if your fuel loads have been managed, when these things start interacting with each other, they'll enhance their own intensity, essentially. Okay, so that's really all I wanted to talk about. That's just some graphs, don't worry about that. That's all I really wanted to talk about. So just to summarize, important things to take away. When we're talking about extreme bushfires, we're not talking about ordinary surface fires. Okay, we're talking about coupled fire atmosphere events, which are driven by particular modes of dynamic fire propagation and involve violent pyroconvection. Because these things have different dynamics to ordinary surface fires, the traditional tools that we have to try and predict the behaviour of fires don't tend to work very well when we're trying to predict these sorts of events. Our research has shown that there are particular environmental factors which make these things more likely to occur. So things like rugged terrain, atmospheric instability, and so on, low fuel moisture content, as opposed to fuel load, are the really important ones. One thing we can say with fairly certain terms is that climate change is going to increase the prevalence of these things, okay? And that really comes down to that fuel moisture influence, okay? Fuel moisture goes down if temperatures go up, basically, okay? So if you've got global warming, increasing temperatures, then you can expect on average your fuels are going to be drier and really dry in these extreme days. So while we've still got a fair bit of research to do to really get at a comprehensive understanding of the problem, the bad news is really that this age of violent pyroconvection has probably only just begun, and we're going to be living with it for quite a while. So that's all I really wanted to say. Thanks to the Royal Society for the invitation, particularly thanks to Natalie for making everything happen. And thanks to you all for listening. Hopefully there was something in it there for you.
Yeah, thank you very much indeed, Jason. That was a fabulous talk. And now I think we have a few minutes left over for questions and answers. So Temi, can I pass over to you, please?
Thank you very much, John. Jason, that was a very good presentation. I think I do learn a lot, even though I'm not a mathematician. So that was very good. Thank you for that excellent presentation. We have a couple of questions in the Q&A chat area. And then before I go there, I just want to ask you one question that I was just burning in my mind that, I know you're a mathematician and you do a lot of modeling to predict fire. So one of my questions that have been burning in my heart is that, what are the challenges, that you as a mathematician do face to accurately predict bushfire occurrence and the behavior, as we have observed in the last 2019-2020 Black Summer fire?
Yes, I mean, the Black Summer was a really, really interesting case because, when you have one or two of these events going, you can sort of sit down and focus on that. I mean, Black Summer, we were just overwhelmed. I mean, there was just so many events happening around the place that you couldn't just focus on one. In terms of the modelling, when you want to try and model these things accurately, the sorts of fire behaviours that I talked about, the way that we model those, well, the way we have been modelling those, is through the use of coupled fire atmosphere models. Now, these are very, very sophisticated and computationally expensive models. So when you're trying to, say, run a model to try and understand what the fire is going to do for the next 2 hours, you're talking about running a model on a supercomputer for probably 12 to 15 hours. Now, of course, that's of absolutely no use to someone who's trying to predict what the fire is going to do in the next 1 hour. So one of the things we've been trying to do is to try and, I guess, come up with models of reduced complexity, which are able to, emulate all these important dynamic features, incorporate those in a way which enables you to get some sort of faithful representation of what the fire is doing, but at the same time have a model which will run faster than real time, so that someone working in an operations center can actually have the model going within a minute or so and get a good idea of what the fire is going to do. So that's kind of where we're at. So that pyroconvective modeling I talked about, that's kind of a first step. So some of the, the vorticity-driven lateral spread that I talked about, we can now model that in about 10 seconds as opposed to 10 hours using these sorts of ideas. But I think there's some real opportunities for bringing in some of the, the new developments in areas like machine learning and artificial intelligence to try and, come up with, algorithms which are able to learn the dynamics of these things and then give you ways of having a model which runs, which is finished running before the fire goes out.
Thank you so much. That was very good. So one of the questions that's been asked from the audience is, why has the prevalence of extreme fires increased so sharply from 2000? That is, the question is basically asking, why do fires increase exponentially?
Yeah, no, that's a very good question. I wish I had a good answer for it. I mean, the obvious culprit is that something's probably happened to the climate. That's where fuels were drier in the past, were moister in the past. The way the climate's changed just means that we're seeing fuels which are drier. There's also a bit of work which has been done, which is looking at the how climate change has influenced the way that dangerous frontal systems come across the bottom of Australia, because a lot of the bad fire activity that we have are associated with these fronts. So you'll have a front come across the bight, you'll have heat wave conditions before it, and then this frontal hit, and lots of instability, lots of explosive fire growth associated with those. So there are a lot of different factors which can combine to perhaps drive a tipping point like that, if indeed that's what's happened. But that's still very much an open question.
Thank you very much. And another question that I think we should think about today is, how do we lower the risk of bushfires, especially in Australian regions where they're very, very vulnerable to this occurrence of extreme bushfires?
So which areas in particular do you mean?
Let's look at Western Australia. Yeah,
so definitely Western Australia has had its fair share of pyrocumulonimbus events, particularly in the forested areas of the southwest, further along towards Esperance as well. And they've even had a couple of events up in the deserts where they get some of those really large spinifex fires going, which are a little bit surprising. But yeah, I mean, if you were thinking about a particular region that was more prone, if you were to draw a line of latitude at about 33 degrees south and a similar one north, these things don't tend to happen in the tropics. So sort of these more sort of temperate climates and the forested areas, which are the ones that are mainly affected.
Thank you. Another question is about the Lynn base asked about the lay down fire attachment effect is the same thing that was seen during the infamous King's Cross Rail Fire Station in London in 1987. So she's asking, is there much crossover study between wildfires and the structure of fires?
Yeah, that's exactly the case. And it's actually interesting because the King's Cross fire in the train station was 1987. That sort of took everybody by surprise in the structural firefighting research community. But there was actually a paper published in the wildfire research community 3 years before that, which talked about flame attachment on steep slopes. So it was actually Dick Rothermel from the States who had sort of pointed out this sort of behaviour before it was noticed in the King's Cross fire. But certainly a lot of the research we've done in trying to understand flame attachment, our starting point was exactly the King's Cross fire. So the first thing we did was try and emulate the simulations that they've done in association with that investigation. And then we basically said, okay, what happens if we now, instead of having a rectangular escalated trench, what happens if we start to talk about a V-shaped trench or something a bit more generally shaped? But yeah, the key effect there is something called the Coanda effect. And I think it's exactly the Coanda effect which drives the attachment in both wildfire cases and structural cases.
Thank you so much. I'm not sure whether we can go on with further questions. I'll probably quickly ask one that someone has asked now about how does the type of impact of chemical composition and smoke and particle size affect health consequences?
Yeah, I mean, I'm probably not the right person to ask that question to, but one thing I have had a few discussions with people involved in, smoke pollution and things like that. And one thing you tend to see in these dynamic modes of fire propagation is the smoke's a lot darker. Now that's because the fire is so intense that it will actually use the oxygen faster than it can be resupplied. And so you get incomplete combustion and a lot of black carbon in your smoke. Now, big chunks of black carbon can't be good for your lungs. I mean, you have things like the black lung in coal miners and things like that. So I think there are some very, very clear health impacts there. But again, nobody's really looked at that in any detail.
Thank you. And I think we can take one more question now before we round up. Someone has asked about how do fire retardants interact with fire dynamics?
Yeah, that's an interesting one because, I mean, we've only kind of just started using fire retardants in Australia, in a sort of large scale way. But the thing you see a lot in the US, for example, is they'll drop a fire retardant along a certain part of the terrain, and yeah, certainly they'll slow the fire down. But what often happens is because you have these dynamic modes of fire behaviour that can kick in, the fire will actually escalate in places where the people dropping the retardant didn't expect them to escalate. Okay, so sort of this anti-intuitive nature of the way these fires escalate. So you'll often see a retardant line put somewhere in the landscape, and the fire's actually escalated somewhere else and basically gone around it. But in terms of how does the fire retardant affect the dynamics of the fire, we haven't really looked at that.
Thank you, Jason. We are running out of time now, and then I believe that some of the answers to the questions being posted will be answered soon, and then they will be added to the recording shortly. So thank you. I will hand over to John now.
Okay, thank you, Temi, so much for orchestrating the questions so well. And Jason, I can't thank you enough on behalf of the Hunter branch of the Royal Society of New South Wales. That was truly a fantastic talk. The work you're doing is extremely important. The really frightening thing, I think, is that graph that on the incidence is exponential. And as you pointed out, this is not the end, it's not even the beginning of the end, this is just the end of the beginning of what's going to be a very serious problem for us in the future. And until we really understand the mechanisms that are driving this, it's very difficult to strategize how we can control it. So it's extremely important, the work that you're doing. And again, I can't thank you enough for such a wonderful talk on this subject. Thank you.
My pleasure.